In this lesson we're going to look at the combustion of alkanes. Now, the combustion of any substance really means the reaction of that substance with oxygen. So here we're looking at the reaction of alkanes with oxygen. Now, before I write out the general formula, what I'm going to say is this. We're going to take as an example some alkanes that you're probably familiar with, and these are principally the components of natural gas. So I've got a Bunsen burner here which is being fueled with natural gas. And natural gas is a gas which is mainly made up of methane. That's the first in the homologous series. But you also get a mixture of ethane, propane, butane and pentane. So it's mainly methane, okay, but it also contains the other alkanes which are also gases at room temperature. Alright, and what we're going to do first of all is we're going to have a look at the combustion of these alkanes, that's to say how they react with oxygen when we have what we call complete combustion taking place. So we'll write that at the top here. We're looking at the complete combustion as opposed to the incomplete combustion of alkanes, which we'll look at in a minute. And in order to achieve complete combustion, we have to make sure that the hole on the Bunsen burner is open. Okay, so that hole is fully open. That means I get a really good supply of air. So I have a rich air supply, that's to say plenty of oxygen getting in and mixing with the natural gas as it passes through the column. Now what you will then see is that the colour of the flame changes when that hole is opened. So when we get complete combustion, we get a nice clean blue flame. All the sort of the orangey yellowy colour goes, and we know that complete combustion is taking place. So what is the general formula? Well, we'll have an alkane plus oxygen will give us what? Well, we remember that alkanes are hydrocarbons. They're made from two elements, hydrogen and carbon. And so when these react with oxygen, you're going to get two oxides produced. One oxide of hydrogen, which you're very familiar with, which is called water. If water had a chemical name, it would be called hydrogen oxide. And the other oxide is an oxide of carbon, which is carbon dioxide. And this is the general formula for the complete combustion of alkanes. But it really applies to just about any hydrocarbon that reacts with oxygen, whether it be an alkane or whether it be an alcohol or whether it be a sugar or glucose, whether it be wax, for example, in candle wax. We're always going to get these two products produced, water and carbon dioxide. Okay, so let's just take a couple of specific formulas. We'll choose methane and we'll write out the balanced equations. So CH4, methane plus oxygen, gives us water plus CO2. So we just need to balance that. We notice that we've got 4 hydrogens here and 2 here. So what we'll do is we'll put a 2 here next to this water. That gives us 4 hydrogens and 4 hydrogens. Now we've got 4 oxygens on this side and only 2 on this side. So we just need to put a 2 here to balance the equation. Okay, so there you've got the balanced equation for the reaction of methane with oxygen. And then let's have a look, for example, at, let's say, just propane. Okay, so we'll have C3H8 for propane plus oxygen, H2O for water. Again, same products, always the same products for complete combustion. So let's balance the equation. Let's have a look at the carbons first. In this case, we've got 3 carbons here, we've got 1 there, so we'll put a 3 here. And then we'll have a look at the hydrogens. We've got 8 there, we've got 2 here, so we put a 4 there. And now we've just got to add up the oxygens. So we've got 4 oxygens there and we've got 6 there, which is 10 oxygens. So I just need to put a 5 there. 5 times 2 is 10. And there we've got the balanced equation for the combustion of propane. Now I should also mention that these are fuels, and the whole point of burning fuels is to get energy. So these tend to be reactions which are pretty exothermic. So we get quite a lot of heat released during this reaction. Now then, let's have a look at the incomplete combustion of alkanes. Now, for incomplete combustion to take place, what we need is a limited supply of air. We're going to need to reduce the air supply, And to do this with our Bunsen burner, what we do is close the hole like that. Okay, what that means now is we've got a much lower supply of oxygen mixing with the natural gas. As a result, the colour of the flame will change. You get this orangey yellow coloured flame. Okay, so hole closed means a reduced supply of air, and this is the standard procedure whenever you have Bunsen burners in the laboratory and you're not actually using them. Then you close the hole so that the flames are visible and you're less likely to burn yourself. Okay, so what's going on here is we're getting incomplete combustion, and when that takes place we have the alkane plus oxygen. We've got limited supply, and now you're getting a number of other products as well as the water and carbon dioxide. So first of all, we're going to get carbon. Okay, that's going to be in the form of soot. Right, so you're going to get tiny little particles of soot appearing here in this flame, and it is in fact those particles of soot which cause the flame to have this kind of bright yellow white colour, because what happens is those particles of soot in the presence of the heat start to incandesce. That means they emit light from right across the spectrum and produce this kind of very bright yellow white flame. Okay, so that's carbon. Now you'll probably remember that you can test this by taking a cold knife or a cold teaspoon and placing it in the flame, and you'll immediately notice that those particles of carbon start to condense on the surface of the cold metal, and that turns black. That will not happen when this hole is open and you get the complete combustion. Okay, so we get carbon plus carbon monoxide, and that's a very toxic gas, and then after that you get the two standard products of the combustion of alkanes, which is carbon dioxide and water. Now it's not likely that in an exam they would ask you to write out one of these equations from scratch and ask you to balance it, but they could possibly give you part of the equation, of the symbol equation that is, and ask you to balance that. So for example, let's take the incomplete combustion of methane. I won't bother writing out the word equation there just to save space, but we need to write out the symbol equation. So we'll have methane, which is CH4 plus oxygen. I'm going to give you carbon plus carbon monoxide plus carbon dioxide plus water. Now there are often a number of different possibilities for this type of equation combinations. I'm just going to give you one possibility, which is this one. Well, you might be given this in the exam and they may ask you just to fill in the rest. So you'd sort out the carbons first. You see you've got 1, 2, 3, 4 carbons there. So you want to put a 4 here. Then you sort out hydrogens. So we've got 16 here. Okay, so we need to put 8 here. And then you need to sort out the oxygens. So you've got 8 there, 2, 2. There's 12 on that side, so we're going to need a 6 here. 6 times 2 is 12, right? And there we've got the balanced equation for the incomplete combustion of methane. Now, just one more thing I need to mention is that the incomplete combustion of alkanes is going to be less exothermic than the complete combustion. So we're going to get energy produced, but we're going to get less energy than when the hole is open and you've got the complete combustion. So let's just make a note of that. So it's less exothermic. That's to say less heat is released. As a result, you wouldn't expect this yellowy orange flame produced when the hole is closed to be as hot as the blue flame produced when the hole is open.